General analysis of a fin heat transfer. So let's consider a surface in which we want to improve the heat transfer rate. So we put an extended surface that in this case we are going to mimic as kind of a cylinder. So, but the area it is not going to be constant. So this is like a general surface that we want to consider. And for this surface, we are going to take a disk, one of the section of the extended surface. So here we extracted, and this is the one that we are going to analyze. So we are going to analyze the heat transfer that is coming, the heat transfer that is going out, and this is still going to continue in the solid, and on the surface we are going to have convection. So we are going to subdivide the heat transfer into three surfaces: the surface on the back, the surface on the front, and the surface on the side. Now, for the surface on the front, we are going to assume that the whole temperature it is going to be constant. That's not completely true. So let me go back to this slide and let me zoom in. And so what I'm going to draw here, it is a straight line. So this is straight line. I'm going to compare it with a line that is an isotemperature line. So we can see that they are not exact. So we cannot well, we are going to assume, but the difference is so little that we can actually assume that the temperature in a cross section it is going to be constant. So that's a little assumption that will simplify the equation and allow us to have a differential equation in one dimension for the fin. So let me go back to this slide. So for this section, this is like a 2D version. So we are going to have the heat transfer on the back, the heat transfer after, and the thickness of the disk is going to be dx, and the heat transfer that is happening on the surface. So we have different areas. We have a cross section area, so AC, the cross section area, and we have a surface area. So this is DAS. So the balance of energy for this disk, it is going to be equal to Qx, the heat rate by conduction that is going in, minus the heat that is by conduction after dx distance, Q of x plus dx, minus the Q of conduction. So these two are going out, so therefore I negative. So this is the Q of convection. So this should be equal to 0. So now Q of x, we can assume that is conduction in one dimension. So Q of x, it is going to be equal by 2 minus k multiplied by dt dx multiplied by the cross-sectional area, but that cross-sectional area, it is depending on x, and x is along the fin. So we are going to have cross-sectional variable if it is variable, could be constant in some fins. Now, to analyze the heat transfer at a distance x plus dx, so we are going to use a linear approximation with the derivative. So the Q of x plus dx, it is going to be equal to the Q of x, so the heat transfer at this point plus the change of heat transfer from this point to this point, multiplied by this distance. So the heat transfer rate, in terms of x, it is going to be equal to plus the q of x dx multiplied by the distance dx, and that's the q of the heat transfer rate at q of x plus dx. So if we replace the value of q of x that we obtained in the first equation, so we have that the q of x plus dx is equal to q of x plus the derivative with respect to x of minus k multiplied by dt dx, and everything multiplied by the cross-sectional area AC, let me put it inside the parentheses, AC, and multiply by dx. It looks like see around. Okay, so now we have to incorporate both results into this equation, q of x and the q of x plus dx. So let me do it. So we have q of x minus this whole result, q of x plus the derivative with respect to x of minus k dt dx multiplied by the cross-sectional area dx, now minus the heat transfer by convection. So the heat transfer by convection, it is going to be equal to minus h multiplied by the area, but the area it is going to be equal to dAs, and multiplied by T infinity, sorry, T on the surface minus T infinity. And everything has to be equal to 0. So now let's have a look to these first two terms. So q of x is going to be cancelled, and so we have on just these two terms. So it will simplify to the derivative with respect to x of minus k dt dx multiplied by the cross-sectional area and multiplied by dx minus h, the area, the surface area, multiplied by the temperature of the surface minus the temperature of the fluid around T infinity. So that should be equal to 0. Now let me divide by dx. So if I divide by dx, so this will cancel and this will cancel. So the final expression, it will be the derivative with respect to x of minus k dt dx multiplied by the cross-sectional area minus h dAs dx T of s minus T infinity equal to 0. So now, so we have an expression in which the first term is the derivative of this term. So this term, it is k, which is a constant, dt dx, and the cross-sectional area. So the cross-sectional area will sometimes depend of x, like in this case that the area, the cross-sectional area, it is becoming smaller. So the surface area also can be depending on x. So let's move this equation to the next page and do this derivative so we can have a full expression. So I'm going to move this equation to the next page. So, and let's continue with the derivative. So the derivative of the first case, it is the derivative of a product. So we have that this is equal. So this is equal to the derivative with respect to x of minus k dt dx multiplied by AC, the cross-sectional area, plus the first term, I'm considering the first term, these two, plus minus k dt dx multiplied by the derivative of the second, so the AC over dx, minus in the second term, we can just probably expand it, so we have h multiplied by the AS dx multiplied by ts, and plus h multiplied by the AS dx multiplied by T infinity, and this should be equal to 0. So just let me get some constants out of the derivatives, and that's the final result. So let's see, in the first case, this constant, we can take it out of the derivative, and we have the second derivative of the temperature. And so let me put the minus k multiplied by this cross-sectional area and multiply by the second derivative of t with respect to x. Now plus k, or minus in this case, minus k dt dx dAc dx minus h dAs dx multiplied by ts plus h t infinity dAs dx equal to 0. So this is the general form. This is the general form of the heat transfer in an extended surface. So we can see that it's a function. It will depend if the cross-sectional area depends on x, and the surface area also depends on x. So the shape is going to be very important. So this is the general form. Now, let's see what happened to the heat transfer rate. Okay, to analyze the heat transfer rate, so we are going to consider the structure, the surface with the fin, and in this case I just separate the fin from the structure. So we are going to have, because all the heat that is coming from the structure into the fin is going to pass through this surface, so I want to account for this surface. So we want to compute all the heat that is going by convection. So this is the Q of convection. So that Q of convection, it will be equal to the Q of conduction in the base. So the Q of conduction on the base, it is equal to the Q of convection on the fin, on all over the fin. So I'm going to call this surface of the fin the area of the fin, AF. And this surface, I'm going to call it the area of the base. Okay, so expanding this equation, so what we have is that the left-hand side, it is conduction, so we have minus K multiplied by the area of the base multiplied by dt dx, so that's the heat transfer rate on the base. It should be equal to the heat transfer by convection on the fin, so that's going to be H multiplied by T on the surface, but T on the surface will depend on the location, minus T infinity, the temperature of the media, multiply by the A of the fin, of the AS, and this is going to be the surface area that we had. The total area, it is AF, but so we have to integrate. So we have to integrate over the area of the fin. So this is the equation for the heat transfer rate on the fin. Now, some definitions that are very useful in this analysis of fins. So we are going to define theta of x as the temperature at some point x in the fin minus T infinity. So the temperature, it will change from the temperature of the base to the temperature of the tip. So let's see it in this drawing. So the temperature, it is going to change. So this is T of S that is dependent on x, and x, it is, this distance is x. Okay? So to simplify that last expression, to simplify this expression, we are going to define theta of x as the difference of the temperature minus T infinity. So if I take the derivative of the theta dx with respect to x, so we have that is going to be equal to the T of x dx minus 0, because it's the derivative of a constant. So I can rewrite that equation using this result as minus k multiplied by the area of the base, the theta dx, because the T dx is equal to the theta dx, equal to the integral of h multiplied by theta of x das, and the integral over the whole area of the fin.